Okay. Hi, Diganta.
Hi. Yeah.
Okay, so let me start with this slide. Okay, just to remind you, so what we did last time was the K induction algorithm. I think this picture is important. So K induction, see, inductive, including traditional model checking and what we're discussing now, doing model checking of safety properties through searching of inductive invariance is what is kind of captured here. There are given an invariant property defined by a predicate P, there are you can there are several candidate inductive invariants that you can actually use and somehow get to prove P. Okay, the forward model checking method that computes the least fixed point as a least fixed point, the reachability state is what I've shown here. A reachable set of states from some initial state is the strongest invariant, and the backward approach of computing, the set of all states that satisfy AG of P is, you as the greatest fixed point gives you, in some sense, the weakest inductive invariant that is strong enough to prove the property. What I've shown here in dotted circles are other possible candidates for inductive invariance that you can actually use to prove the property. And if there are ways to get to it, in an efficient fashion, then that will be a better method. Now, between these two approaches, the forward approach of computing the reachable set of all reachable states and then doing it, and the backward approach of starting from P and then getting the greatest fixed point, which would be better, you think, Paramalai?
I don't know, sir.
Huh? What was your answer?
I don't know which one.
Okay, let me give a hint. So when I say better, I mean in terms of performance. Okay, so the performance here means the number of iterations it takes for you to reach the fixed point. That's how you have to compare. Okay? I mean, that is one way of comparing. Of course, in trying to do that, you build BDDs, and therefore the largest BDD that is ever built, that's also thing. So in terms of, let's look at iterations, okay, because the number of iterations in some way also tells you number of intermediate taus that you will have to generate. Okay, for this reachable, for computing the least fixed point, what is the number of iterations you need? Last time we had the threshold. No, what was that? That is the diameter.
Yeah.
Okay.
Okay.
Now, this backward approach, what is the thing needed? So recall how the backward approach does. When you compute the greatest fixed point, you are removing things that should not be in an inductive invariant. That is what I call as counterexample to induction. So if there are P states that in one or more steps get you out of P, they don't belong in a fixed point, correct? So what it does is it kind of removes the thing from P. So the largest, in some sense, it is the large, it's a reachable diameter. It's the largest diameter from any P state, the largest reachable, distance from any P state to a non-P state. That is a not P state. So if you remember that this was the initial diameter, okay, that you require, whereas this one will be the the reachable diameter, the reachable distance, the longest reachable distance from any P state to a not P state, because that's what it keeps removing in each iteration until it removes all of them. So the answer to my question is, it depends, is the answer. If indeed this initialized diameter is small, then this works out better. If the other one is shorter, that works out better. So there is no clear-cut answer. It all depends on the property and the structure of the transition system. Now, the K induction, as we saw, was a technique which uses the backward approach, but instead of computing images, the descending tau images till it gets a fixed point, what it does is, as I showed, it does an inductiveness check, incrementally longer and longer inductiveness checks, okay, to check if it is one inductive, the property is one inductive, two inductive, and so on, until for some K, it may discover that it is, K inductive, and we saw that that was equivalent to actually doing this backward thing, okay. Although it does not compute images, but that it does longer and longer K inductive checks, and that K can be this longest, actually the longest part until it kind of folds itself, okay. So in that sense, it can be, yeah, it is the, because it is doing the checks, so until it folds itself. So it is actually the reoccurrence diameter from a P to a not P, okay? From P to a not P is what it does, okay? This is not what I wanted to get, okay? So, yeah, so this is, like I pointed out, yeah, so each inductiveness check at K really says that if I assume that all the things that that take it away from a P state, away from a P, from P into a not P in K steps, assuming that, is there one more step, okay, to check that. So when all of those things kind of fold back into, so in that sense, it is actually the reachable, diameter also in there, okay? Yeah, from a P to a not P state. So in any case, so what you will have to do, the algorithm has two components. One is while you're doing this inductiveness check, longer and longer inductiveness check, you also need to check for counter examples, because your system could be unsafe, okay? So it does these two things simultaneously, okay? If there is no, K long counter example, let's see if you've reached a fixed point by doing a K long inductiveness check. If so, then it will do things. So, I mean, this should actually be reachable, okay? Reachable distance from P to a not P state. And that's how it does things. And of course, if it is safe, then it'll take those many from P to not P, a state that you require. If not, if it is unsafe, then it will take whatever is the longest counterexample distance from any one of the initial states. Okay, so that's how that's how it does. Okay, so yes, and there was one other point that I mentioned as well, which is what is that? This is incomplete. Why is it incomplete? That if it terminates, then it successfully either finds a counterexample or completes. Okay, the model checking. Okay, but there are reasons why it may not terminate. Amin, why does it not terminate? In that sense, it's incomplete. Why might it not terminate?
I
mentioned it last time.
It could go on forever, right?
Yeah, that's right. But I'm asking, go on forever means
yeah.
I'm asking the reason why it doesn't. But this check, the inductiveness check, is only is a sufficient check, but not necessary, because for examples like this, when you're trying to check if Q is an invariant, but it's not an inductive invariant, it's a two inductive invariant. If there are paths from P states, that is the property, states in which the property holds good, in which here the property is, invariant property is Q, to a not P state that may not be reachable, okay? In this case, Q is not reachable, but because there is a self loop here into itself, or in general, if there is a loop from, one or more, one or more long, in this case, it's a self loop, then there'll be in infinite paths, longer and longer paths from incrementally longer and longer paths from a Q state, that is a property state, to a not P state. So, but the inductiveness check only checks if if it is inductive. Okay, so you also need to ensure you have to have strengthened the induction hypothesis with a loop check. Okay, that it is enough. Okay, it is enough if you as long as you in the inductiveness check, you only need to check paths leading to the thing without any reoccurrence of the state. Because if there is a if as long as there is the shortest path without any reoccurring, it is still it would still eliminate that in any case. But you will need to have a check for for that to avoid this kind of situation where so where you have yes, where you will end up. So it is actually, that's why. So from a P to a not P state, you will have to ensure when you check that it is enough to check if on paths leading from a property state to a negation of the property state without any reoccurrence of that thing. Otherwise, the inductiveness check continues to fail for longer and longer K. So to make it complete, you need to add this condition as well, in addition to this one. Okay. Of course, checking a loopness condition is harder than just the simple thing, because that has a formula of quadratic size, okay, because it has to do pairwise comparison of the state. So sometimes some implementations of K induction, just do it for incomplete. You use the incomplete, live with that incompleteness. Okay? Okay, so yes, that's what I want to end with here. If you have any questions here?
I have a question here.
Yeah.
So in the example question,
Which slide you want me to get to?
on the last example we have seen,
Okay.
the example,
Ah,
the last slide. Yeah, this one. Now, assume that the states 6 and 7 are not present. Now, if the system consists of only the first 5 states, then AG of Q holds, right? Because
actually, AG of Q holds here regardless. Okay?
yeah. So my question is, in the algorithm, when K is equal to 1, Q will not be an inductive invariant, right? Because it has a state 4 to 5. Then the method will return a counter example, right?
No. Look at the counterexample check that's being checked. It has IS not.
Okay.
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 It's only it's a counterexample only if it is reachable from one of the initial states. That's why the base check, okay, the counterexample check is the standard BMC check. The inductiveness check is from arbitrary state that satisfies P.
Okay.
Okay, that's why it's this pathological situation ends up happening for the inductiveness check. Okay, so the inductiveness check is saying, oh, have I reached, okay, some point where if I assume P holds good for K long path, if I fold back into itself. Okay, but that is as a SAT check. This is sufficient but not necessary.
Yeah. Okay, sir.
Because you're starting from an arbitrary. That's why the counterexample thing always checks from an initial state. And this is not an initial state, so this won't happen. Yeah.
Okay.
Yeah. So that's a very important thing. The counterexample check starts from IS naught, K long, whereas the inductiveness check, which does a completeness check, whether I've reached, whether there exists a fixed point through a SAT check, is starts from an arbitrary state that satisfies the property. Okay.
Okay.
Yeah, and for that, that's why there could be these kinds of things. Okay? Because since the arbitrary state that you check the inductiveness check for may not be reachable. Okay. So, like for example, it will indeed include So it can include some unreachable states. As a matter of fact, it will. No, in this case, it does not. Okay, so it can include. In this case, it'll exactly include. Let's suppose that you had another state here, which is not reachable, but is is something that goes into for the simple reason. Let's suppose that you have a state here, a Q state, which just goes back to itself. Now, that is not reachable, but that still will be in the inductive invariant. In the inductive invariant that it generates. Okay. In the backward propagation. You see?
Okay.
Yeah, because the greatest fixed point, AG of P, will have things, okay, that may not be reachable, but they are not counterexample to induction. Okay. So it will have all those kinds of things. So that's an important point that I just now made, okay, which you will see that we will exploit. Okay. So when I pointed this thing out, so here this fixed point that I'm moving the cursor over corresponding to AG of P, will have a lot of unreachable states, okay? Because lots of unreachable states, but they're all not counterexample to induction because all of them never go outside of that, okay? Therefore, it has a lot of unreachable states, but they are safe states, okay? And they're okay to include, to keep them in your inductive, in your inductive invariant. That is, and you could still, that is strong enough to prove the property. That is what you're trying to exploit when you try to get to other inductive invariants. As a matter of fact, and that's what happens there, okay? Yeah, did you get the point?
Yes, sir. Yeah.
Okay. And that's why maybe looking for other inductive invariants that are weaker than the, the strongest, which is the reachable point, may get you may be a more efficient search. And all these the two other inductive model checking method that we will see are one, they look at other, candidate inductive invariants. Okay.
Sir, one more question.
Yeah.
How are you saying that the K induction works similar to the greatest fixed point in the algorithm you provided? It's just
Yeah. How do I say that?
so can you show the algorithm, the last slide?
Yes.
Here the index method doesn't behave as a greatest fixed point.
No. Here we are not computing the greatest fixed point. But what I'm saying is, when I reach the point where the inductiveness check succeeds for some K,
Okay.
then at that point, there is proof. I mean, the inductiveness, what is the, eliminated all, paths or states leading, starting from P to a not P. Exactly those. Here, like I've shown here.
Okay.
So the first check, I will check if it is one inductive, okay? If P itself is a fixed point. If not, if it is one inductive fails, there is some state from which there is, a successor is outside P. So when I do the two inductiveness check, I'm kind of indirectly, saying, let's only assume those things in which P is true, not only P is true, but also its successors are all in P. Under that assumption, will I fold? Okay. So each time that's what it is doing. So if I
Okay. Yeah, now I get.
I'll get to this. Yeah. And
Yeah,
this is exactly AG of P. Yeah.
Okay.
Yeah. Okay, so now once again, let me get to this. So the first thing that we'll do is model checking with interpolant. Okay, there are several things, several methods that leverage interpolants to do inductive model checking. Several methods. We'll be looking at one, which uses this idea. So again, I'll go back to this thing. See, if I exactly do forward least fixed point cleaning iteration starting from the initial state, I get to this, okay? The strongest inductive invariant reachable states. Now, if somehow, I mean, if I start with not with I, but some over approximation of I, that is a superset of I, and I do cleaning iteration, of course, I will always reach a fixed point. Now, if the over approximation that I choose, of course, that that fixed point that I get when I do a cleaning iteration, forward cleaning iteration, will have some unreachable states. Okay, for example, if I want to compute the fixed point of the dotted line, I can start with an over approximation of I, do cleaning iteration until I get that, and that will have, of course, some states that are, some states that are not in the initial state, and as a consequence, also states that are unreachable. Okay, but if they happen to be not harmful states, that they all happen to be still P states, then that is okay. That is good enough for me to prove that, because it includes I. Okay, since I'm starting from an over approximation of I, for any safe system, as long as I start from an over approximation of I and then computes its fixed point, that is also good enough. But the question, but the challenge is, how do I know before how do I guess the over approximation? Of course, I mean, the hope is that if I start from a larger over approximation of I, then the fixed point is probably, I could reach the fixed point faster. So the first idea of this interpolant method that I'll discuss is, why not start with an over approximation of I? But the question is, what over approximation that I start out with? If I'm not careful, if I include in that over approximation states that I might get me out of P, that's not actually good. But I won't know ahead of time until I compute the fixed point what elements that I can actually include in the over approximation of I is, that I can use to do the tau iteration. Okay, so the question is, so the idea behind that method that I'm going to describe, which is to use this Craig interpolant, okay, to get an over approximation that is safe. Okay, a safe over approximation. That is the key idea in that. So that starting with I will start with a what I call a safe over approximation of I. Safe in the sense that all reachable states from that over approximation will still lie within within P. That way, that I may be able to use that over approximation to converge faster. Okay. Did you get that? So that's what we will be doing. So I will start with first.
So
yes, tell me.
The over approximation is done so that we can reduce the number of iterations, right?
Okay. The hope, yes, yes.
Yeah.
That is the idea, exactly. Okay, first the definition of Craig interpolant. Okay, so given formulas A and B over some set of variables, A over some set with some common variables. A could be over some set of variables, B over some set of variables. We'll assume that there is some common variables between A and B, such that A and B is false. An interpolant for AB is a formula A prime, such that the following conditions hold good. A implies A prime. That is, A prime is a superset. A prime is an over approximation of A. And A prime and B still unsatisfiable. That is, A prime and B still false. That is, yes. So A prime, the set of states characterized by A prime, still does not include any B states. And a syntactic restriction that A prime refers only to the common variables of A and B. Okay. For example, say A is this formula which computes the one-step image Okay. I mean, yes, it's not an actual image, but it characterizes one-step image starting from IS. Okay. It's defined over, yeah, it's a one-step DMC, okay, formula. And B is, the property, the bad state, which defines bad state. P is the property, and that is defined over S prime. Now, an interpolant is an A prime that satisfies this condition. That for every S, this implies A prime of S prime. So A prime, so the common variable between A and B is S prime, okay? So we require that the interpolant actually ranges over only the common variables, okay, between those two. And A prime should still not include any bad states, okay? So in the context of images, what this means is, this is what, what it says, okay? Suppose my initial state is this, and A, set A is the image of I, one-step image of I under T. Now, A prime, an interpolant, can be some over-approximation of that one-step image, but still is safe in the sense it does not intersect with the bad state. Okay, P, I'm assuming, is the predicate defining the property, invariant property, and therefore it still does not. It is an over-approximation that is still safe. Okay, an interpolant is one such, gives you one such, over-approximation. So interpolants are used in proof theory all over the place. I mean, lots of different things. You guys did learn, Kumar did cover a resolution proof and DPLL in your logic class, correct? Hello?
Yes, but
yeah. So you
I
at
don't
least
remember much of it.
Yeah. Okay. So, no. Yeah, but at least there is a proof, a resolution proof, resolution principle. DPLL is, actually is a special kind of resolution proof. Okay. Given a resolution proof of a contradiction, okay, in this case, you can actually, the fact that this and this A and B as defined below, A and B is false. That's a contradiction. So if you have a resolution proof, an interpolant can be extracted from fairly efficiently, in the sense it is linear in the size of the proof. Okay, given a resolution proof, you can extract an interpolant. Okay, that is an A prime. I mean, and you can have lots of different interpolants. Okay, depending upon what resolution proof that you actually use. Okay, and there is always an interpolant. Why? A itself serves as an interpolant. Okay, because so A is always an interpolant. But the idea is we want to get weakest, some very weak interpolants. That is what then we'll get safe, fairly weak over approximations. Okay, so that is the idea. So in A prime, an interpolant is an over approximation of one-step image, yet it does not contain any bad states. In that sense, it is a safe. Now we can extend this concept to a K step, K step safe interpolant. Okay, so just something, Craig, long time ago. Okay, this is probably in the 1950s or something like that. Showed that existence of interpolants for all first order formulas even with interpreted entities, not just for propositional thing. And he also showed that it is quantifier free if A and B are quantifier free, and they can be extracted from a refutation proof. Okay, that is an unsat proof for propositional logic. Similar to unsat core extraction and in the linear in the science. Okay, and there are lots of theorem provers now, and even sat solvers which provide this as a service. Okay, as a feature, and people have extended extraction of interpolants to beyond propositional logic to other kinds of theories that include uninterpreted functions, equality, and linear inequalities. Okay. So in the context of bounded model checking, and how we could actually use this to find safe over approximations to get to other weaker inductive invariants than reachable state, here is something that I want to bring your attention to. So let's suppose instead of B, the B we chose in the last line as just the bad state. Instead, let's suppose that we split the BMC formula this way. The one step, A is the one step part, and B is the remainder of the K step part. So the common variable you see is still the S1 variable here that you get after the one step image. This is exactly the BMC formula whose satisfaction reveals existence of counterexample. Okay, it is checking if there is some bad state, not P, in any one of the states reachable in up to K steps. So an interpolant of these two formulas is what we define as a K-safe interpolant. And this is just exactly just the formula that has changed. So this A prime that you get, the interpolant, will still will still imply not B, and not B is this. Okay, so you still, if you so any state inside A prime will not get to a bad state, but up to K. Now this whole thing is K plus one path. There's 1 plus K, so up to K more paths, it will never get into a bad state. And that's why I call this as a K-safe interpolant. Okay, it is an over approximation of the first step image, which guarantees that up to K more steps, it will never intersect. Okay, so this is what in picture A prime. If there is such an interpolant, okay, then it will be. So, up to K, long thing, the states inside this will not get into not P. So the idea is, okay, now why not use this as an over approximation? So, but how do you use this? What is the check that you do? See, if a K-safe interpolant that you get A prime. So, for example, take the one safe interpolant, okay, that I'm showing here. If that itself is contained inside I mean, it is an inductive invariant. So when you compute the over approximation, if that itself falls back into your I, inside I, that it is your found the thing. Okay. Therefore, and this more generally, this also holds good if you have an K1 safe interpolant, say, which is not inside I yet. If it is inside I, then you know that over approximation, when you I union, that over approximation will be an inductive invariant. But if it is not, then you could run it for K more steps, K1 more steps, or K2 more steps, and then check, starting from I union AK1, and then see if that is included. Okay, so with just K long BMC kind of a formula, you keep computing the interpolants, over approximations, and then see if I take the union of that, of that interpolant and the initial state, if that is included in the initial state itself. Okay, so then, yeah, that is the idea here. with that, not only using one key idea is using interpolant to compute over approximation, and actually iterating with that over approximated I to see if I can keep computing the interpolants to see if eventually I will, there's some greater than k, which I've used, for some multiple of k, after which the over approximation that I get as an interpolant, when I union all those things, will fold back into my original initial state, in which case I have reached a fixed point. Okay. So you see here, what I'm checking is at each step, if I run it up to get a k state thing, then that initial I union, if I further compute a k step interpolant from that thing, if that is contained inside I union k. So I start with I, then compute a k safe interpolant. I union that with the I, and then do a k more. From that, I will compute another k safe interpolant over I union ak, and see if if there is some k that is greater than for some multiple of k for which this that interpolant itself is contained in the initial state, then I have reached a fixed point. Okay, and that's what you check. Now, of course, it doesn't have to, because although you're using a k-safe interpolant as an over approximation, there's no guarantee that just because you increased k, you will end up getting a fixed point. Okay, that's once again, that's a kind of a guess. Okay, but there may be, maybe if it is if it is a safe thing, then there might be some larger k. But if it ends up while doing this iterative interpolant search, that if it ends up intersecting a bad state, then you cannot say anything about it. And therefore, at that point, you have to increase your original k. Okay, so what I'm doing is I have to pick some k. Okay, and I will put it to use. If you know that there has not been any counterexample up to k, then you can see if there is a k-safe interpolant with that k. And you can maybe put that to use, okay, in doing this iterative interpolant search for a over approximated, for generating a candidate invariant from an over approximated initial image. Okay, so that is the idea. Okay. Okay, so here is the procedure, which is actually given in the book. This is all in chapter 10. All this discussion that I'm having now is the topic of chapter 10 in the book. Okay, so he calls it as CraigReachability. So S0 is the initial state. Okay, any questions about k-safe interpolant? I mean, you have to be convinced that if AK is contained inside I union AK, that it is indeed an inductive invariant, right? Because if every state inside that over approximation is itself inside I union AK, then nothing can get out of further K steps, correct? Okay, so you're with me on that? And that's the check that it is done. Okay, are you with me on that?
Yes, sir. Yeah.
Okay. So what this does is, of course, you will so you will start with an initial state and a bad state, not P. The initial state itself intersects with a bad state, then you declare it is unsafe. Otherwise, you start with this CraigReachability for K is equal to 1. and you initialize Q to the initial state, and you do this. You do this until you either declare it safe or find a counterexample. What it is doing is you build a BMC formula for just like you're using a bounded model checking. Okay, A and B is your standard BMC formula of size K, starting from K is equal to 1. Now, and of course, I have split that into A part and B part. A is the one-step part, and the B is the remaining part. Okay. Then A and B. In the beginning, of course, B will only have the bad state. After that, so if A and B is sat, then because I'll be doing this not only for I at the beginning, I'll be doing for S0, the initial state. Okay, initial set of states. As I move along, I'll be over approximating. That's why there is a check here. So if A and B is sat, then I have, if I'm still working with S0, okay, with the BMC, then it could be, so that there is a potential counterexample. That is if Q itself is still my initial state, then I know that I found a counterexample, okay, a K-long path to a bad state. Therefore, I declare that the system is unsafe. Otherwise, I increase K. And then, yeah, no, here you see, if indeed, in this case, I mean, let me come to this part later. Okay, if A and B is not sat, okay, right in the beginning, you will do a one-step counterexample, two-step, three-step, and so on. And let's suppose that it is unsat, which means that you're not found any one-step, counterexample. Therefore, at that point, what it does is it puts that unsatisfiability of the non-existence of any one step. In the normal K induction, you would have just proceeded to K is equal to 2, okay, to see if there are larger counterexamples. But here, what you do is you go into that interpollant computing loop, okay? Since you know that there is A and B is unsatisfiable, that there is no one long counterexample, or some in general, some K long. You can run it up to K, and then you can do this as well. So then you compute the interpollant I here is interpollant. The initial state is S0. I is the interpollant of A and B. Okay. If I do this immediately after K is equal to 1, I'm computing a one safe interpollant. But you can do this after some K also. Okay. So, and then I'll check if that interpollant itself is contained inside my initial state. Okay. If the interpollant itself is contained, in the initial state, then as I observed that you have reached I itself is a fixed point. If not, then I will add the interpollant I. Once again, I is not the initial state here. I is the interpollant. Okay. So right in the beginning, Q is initialized to S0, and therefore I will just take a union of it, and then I'll compute a further K safe interpollant. Okay. To see if with that K, I have reached, but I'm doing this with one moment, please. Yeah. So, Seri. Okay. Okay. Pandra. Yeah. So what you're doing is you're putting to use whether at that K you have reached a fixed point. I mean, in the K induction, you would have used the K long inductiveness check. Instead, what you're doing is you're using over approximated iteration using interpollant to check if I've reached a fixed point. okay, using over approximated thing. But if I end up, if that k is not, if I cannot, because that k might have, is not, if it ends up intersecting with the thing, then what I will do is, no, I will have to go back, start afresh from the initial state, kind of increase, okay, with, longer, k. Because see, this check itself will not reveal, because it's an over approximated image. Just because it failed here, it doesn't mean that there is an error, okay? Because maybe, yeah, so you'll have to go back to see if the failure of this is due to existence of a true counterexample. And therefore you go back in here and then you increase the k. Start from afresh, from the initial state, S0, and then you can build a BMC formula which is longer than k. Okay, and the way I've shown, the algorithm shown here is, for each k you will do the over approximated image computation to see, over approximated interpolant computation to see if you reach a fixed point. Okay, that's what you do. Yeah. Okay. So either this will end either with a discovery of a counterexample for some k, or it will, if it is, safe, then with that iterated k thing, it may end up. So the best way to run this thing is to kind of not do this for every increment, every k, which you can do as well. You kind of do BMC check for up to some k, okay? And then say you're running out of steam. And after that, you may want to put to use the unsatisfiability, that is the lack of existence of any k-long counter examples, to better use. Okay, there you will do this interpolant-based accelerated inductiveness check. Okay, and if it fails, then of course it is because there could be some other counterexample of a longer path which you will have to revert back to. Okay, so any questions here? Okay. Yeah, so the advantages of over BMC or standard MCC, of course, this you already know. K induction itself has this. But over K induction, once you know that there is no counterexample up to K, what you do is you're learning from the unsatisfiability of BMC-K, okay, before you increment K. And that step you do purely by computing interpolants, okay? Interpolants for repeated over approximations of your initial state to see if you are doing it. Therefore, you see this BMC-K, you're starting at K, and then you are putting that to better use through interpolant. Okay. After that, this inductiveness check in K induction itself is incrementally longer and longer. Whereas here, just with the K long unsatisfiability, you are checking with interpolant. Of course, you'll be computing a series of interpolants. Okay. Doing interstellar computation, but all that is done just using BMC, with that, yes, the interpolant things, okay? And the hope is that the interpolant computation is efficient. The worst case number of iterations is still bounded by the reachable diameter here also. because simultaneously you will have to be checking the unsatisfiability of the thing. So over K induction, I guess it's the same. It's the same thing. You're leveraging the unsat effort, I mean, of BMCK before you increment the K. Okay. Okay. So then I have some examples here, which I think I can defer right now. See, because I want to quickly go through. Let me see what the time is. Yeah, I still have time. So unless I refresh you, I have these examples of that illustrates this thing, okay? But in order for you can go through this example, okay? But it also shows you how to extract an interpolant from a resolution proof, okay? That will require for me to go through what a resolution proof is and so on, okay, which I'm willing to do, okay, and if there is interest, I will certainly do it, since I want to but I want to do it after I go through and yeah, so you need to understand that in order for for you to understand these things, because this algorithm completely. So just you won't be able to review this on your own. Yeah, unless you have a good understanding of the resolution proof. Okay, so I will defer this to later, but I want to quickly get to talking about the PDR, property directed reachability, in the next 10 to 15 minutes, just an introduction, and then I will get to more details in the next class when Ratnakar is also back healthy. Okay. Yeah. So as I said, K induction gets AGFP. Okay. Just yeah, and the interpolant based thing, it'll get to one of these kind of possibly dotted circles using interpolant to start iterating with an over approximation of I. Now, PDR can be considered as a method which actually does several things. Okay, what inductive invariant it gets to is very much depends on it combines lots of different things. It kind of exploits the structure of the formula, the clausal structure of the formula in SAM. First of all these methods that I'm discussing now, starting with K induction and BMC, are SAT-based methods. So when you're dealing with SAT solvers, you assume that all the formulas that you're talking about are in CNF form. Okay, so here it exploits a few really neat and very clever concepts to kind of do a kind of, it exploits the structure, the clausal structure of the thing, and does very incremental thing, does certain local searches for local fixed points. They may not be the overall fixed points, and then try to get quickly to any one of the inductive invariants. Yeah, I really don't know if there is, it very much depends on so many different factors that it exploits as to where it gets. It certainly does not do either forward or backward. It is some kind of a mixed kind of thing. I mean, we can discuss as to what the thing is. I also do not have very clear answer to which inductive invariant that it actually gets to, but it uses a potpourri of clever techniques to get you to that inductive invariant. Okay. Having said that, here are three key ideas behind property-directed reachability. See, in both K-induction and to some extent even the interpollant-based induction, the inductiveness check is done on a K-long formula, which has K copies of your transition relation. And another thing is, all those methods, they start with, for example, either the forward-based methods, they start, or even the, there is a single candidate invariant that it works with, okay? Whereas here, it keeps multiple candidate invariants, all in CNF form, like I've shown here. F0, F1, F2, and some up to some Fi at some point. Okay, instead of just building K-long formulas, it kind of, as reminiscent of your image computation, it kind of keeps copies of these things. Okay, but these are candidate invariants. Okay, that's yeah. So F0 is your initial state, initial predicate, and F1, F2, and Fi are, here they're called frames, they are CNF formulas, but they're over approximations to images that are derivable in K-steps. Actually, yeah, so they actually satisfy. I mean, the algorithm maintains at any point I frames, okay, I predicates, which can be potential candidate invariants. They satisfy these four properties. The algorithm is structured, is defined, is described such that it preserves these invariants. Frame F0 is always the initial predicate, right? That never changes. And the series of frames Fi is monotone. That, as I've shown here, Fi is contained in Fi plus 1. That is maintained. All of them, yeah, none of the frames contains not P. Okay, all of them are P states. Okay, that is maintained. The fourth one is Fi plus 1 is an over approximation of the image of Fi. Okay, that is, image of Fi is contained in Fi plus 1. The idea of keeping these, several copies of it is you're still keeping it in CNF form. You're not exactly, as you will see, but they serve the purpose of, you could say the towns that you kept track of in actual, they are something like this, like that, but there you're computing exact image computation. But here you're doing, you're keeping over approximation of the images. These four things are maintained. And notice that these are all over approximations, okay? And they all contain images of up to I step. The reason I say it's candidate invariance is that they may also contain, although they all contain only P states, they may contain, until the algorithm really grows this frames, okay, incrementally, one by one, and until it gets to discovering that one of the FIs may have become an actual invariant. They are only candidate invariants. They are not really invariants. In the sense, they all, see, whenever you have some P, set of P states, okay, which is a subset of P, when is it not inductive? Where am I lying? What makes it not inductive? That's the question I'm asking. I've already shown that in this picture. If it contains some counterexample to induction. After all, these are P states, okay? So they're all potential candidate invariants for proving P. But if they're not inductive, that means, what does it mean? They have counterexample to induction. That means they have some state which gets you out in one or more steps to a not P state, as I've shown here. They may all contain the images, like I've said here, but they're still only candidate, which means they have states like this that are included in that. So they may have some P states that in one or more steps get you out of not P. Now the idea is to get rid of those things. Okay, well, that is the standard practice. As a matter of AG of P, K induction, all of them did the same thing. But here you do it by maintaining whole sequence of frames. How do you do that? Key idea 2. Okay, the algorithm has a blocking phase and a forward propagating phase. Okay, the blocking phase does what are called frame strengthening to eliminate counterexample to inductions of longer and longer, longer and longer counterexample to inductions. Okay, but the other idea, okay, and that is the reason why it keeps track of multiple frames and not a single candidate. The idea is every SAT call that it uses in the process involves only a single copy. It is a SAT call involving a formula which has a single copy of the transition relation on. The idea is it is trying to exploit. See, SAT solvers are, so their complexity depends on the number of variables and number of clauses. The smaller the size of the thing, the better is the SAT performance. So even if it means that you want to do millions small SAT checks, it is better than, it will be faster doing million small SAT checks than a single SAT check that has million variables, a million variable instance of a single SAT check. Okay. Therefore, what it does is, it is doing kind of memory, time trade-off. Okay, I will keep several candidate invariants, but I will, reduce this elimination of CTIs, which was done in AG of P in the greatest fixed point by eliminating counterexample to induction by keeping track of images. In the case of K induction and the other thing, it was doing by longer and longer K, instances, K long thing. But here, every check whatever check that you do has one instance. Okay, and how does it do it? It actually does somewhat similar to this. Okay, it's the time for 40. Okay, so don't worry about getting the details here. All it does is, so at this point, so each of these FI, after these counterexamples are eliminated, this frame FI would have gotten it from it all counterexamples to induction of I long eliminated. Okay, so the way it does is, so when it introduces a new frame, what are the counterexample to induction in a new frame? When it extends this, those are states that get you to a not P state. Okay, so that needs to be eliminated. Okay, so what it does is, so it'll check, oh, can I, since it has maintained these earlier frames, it checks, oh, is some state, some P state from F2. So every time you start a new frame, you start with, you get rid of all the not P. That is easy to do. You always start with P. Okay, and then you see if there is a counterexample to induction, one-step counterexample to induction there. Okay, that is if there is any state that is getting that you are out of into an not P. If so, that needs to be eliminated. So you have to strengthen this FI. Okay, so but that you need to do. But for that, what it also does is, there could be it checks if there is a predecessor. I mean, a state in F2 which in one step reaches that. Okay, if so, then it'll eliminate F that the predecessor from F2, and so on. Okay, and it checks backwards. At each step, it is only doing this reachability check, one-step reachability check, to see if it is, because it has maintained these frames, it is checking only one reachability of a state from Fi to Fi plus 1, from a state in Fi to a CTI in Fi plus 1. Okay, and that's what it keeps doing. Now, in that process, if it hits F0, then you know that you have reached a real counterexample. If not, then you have to eliminate those. They are true counterexample to inductions, and therefore you have to eliminate them. Therefore, that it does by so as long as there are counterexamples to induction in each of these things, it eliminates. As long as there is a predecessor, that is reachable, then it eliminates that until it so that it does in a backward way. If it is not a true counterexample, then that kind of backward chain will get blocked at some point anyway. So that'll actually stop, and therefore you would have in the process eliminated all counterexamples of I plus 1. Okay, so it starts with F1, F2, and so on. This is the blocking phase, okay, in which longer and longer counterexamples to inductions are eliminated. Okay, now, I mean, some of you might be, you must be wondering, what is the big deal? After all, AG of P does this thing too, and K induction does it in its own way, although it is not computing images. Okay, but the difference is, at this point, by the uniqueness here is it maintains these frames so that each reachability check here is only one step, and there is no existential quantification elimination over a large formula. Okay, and those are the two things. Now, you could keep on doing this and then get to something at some point you will get to some in Fi, Fk, at which point you would have eliminated all CTIs. Okay, then it is no different in some sense than what you did with AG of P, except that you did not explicitly use existential quantification elimination. Okay, but in terms of the number of frames that you have to build, you would be doing the same thing. So, but of course, you could use. There are lots of optimizations you can use even in this step. We will get to that later on. But the critical, okay, this is the third idea that it uses. The first two ideas are just to I've already mentioned, so I won't repeat. This is the critical idea. This is where it learns something called relative inductiveness. So by the way, I don't know if I didn't show you the first one. Okay, this one was when it was invented, when it was first introduced, that way. This was by one guy called Aaron Bradley, who was a student of a famous, verification person named Zohrman. I'm not even sure if Zohrman might have even, I don't know if he has got a Turing Award or not. So this was done. He was Aaron Bradley did it for his PhD work at Stanford under Zohar Mana, okay, done in 2010 or around, okay. And Zohar Mana is a very, very big name in theorem proving, model checking, generally verification, programming logics, what have you, okay. Aaron Bradley is a very, very interesting guy as well. So, he could have, and this particular algorithm became very, very, its implementation, especially for hardware application for proposition logic based thing, is still the fastest and the best model checker that exists. Okay. And, Aaron Bradley could have made his calling, and he could have gone anywhere, but he wanted to teach high school students, mathematics, okay? And so he became a high school teacher. And of course, he still holds a position at University of Colorado. He went back to his hometown, and he's a very simple-minded guy. And I never seen anyone like, like him, who's so down to earth. And he still teaches, he's a math teacher at a high school and does some, research occasionally, at University of Colorado. But there's something that for which he became very famous. That's a bit of a history. The third thing I will end in very soon is in doing this. There is also a forward propagation phase in which, see, this one, the backward blocking phase, always one is it identifies and extracts counterexample to induction and then eliminates them by strengthening each frame by the negation of the counterexample to induction. Okay? Unless, of course, it ends up going all the way back to hitting F0, in which case it will end. Okay? But this one is a way to forward propagate clauses from things. So the backward propagation propagates clauses, and the forward propagation propagates clauses in the forward direction. So what it does is, see, a clause Ci in a CNF formula is said to be inductive relative to a clause, entire formula, if with respect to phi, this F should be phi, if phi implies that clause. So phi, I'm assuming, is a CNF formula, means a set of clauses it has. If any clause in that phi, if it is implied by the formula, then it's said to be inductive relative to the clauses in the entire formula. See, a clause in a formula in a CNF form is inductive if every clause is relatively inductive, correct? Because if every formula is relatively inductive, then C1 and C2 and C3 implies C1 as well as C2 as well as C3, and therefore, so it would satisfy the one-step inductive step check. Okay, I'm sorry. When I say this implies, oh, there is something big thing missing here. C1, C2, and C3 and transition. You take one-step transition. After that, C1 holds. Okay, sorry. It is not just implication. So phi here contains the original formula Fi and one-step transition. Okay. After that, this is Ci prime. I should say phi and TSS prime implies Ci prime. Basically, the prime is on the post variable. Is that clear? That was a mistake here. Okay. So that is when it is considered. It is relatively inductive. So a CNF formula is inductive if every clause is relatively inductive. Now, even when it is not relatively, when the entire thing is, as long as a clause is relatively inductive, you can actually propagate that forward without actually violating any one of these invariants. Okay. And that you will see, you need some intuition. So even though this is not fully inductive, still it is kind of close to being inductive, and therefore it kind of that is something that eventually any inductive invariant will have to satisfy. Okay, and you will see why. Okay, as it gets strengthened by removing CTIs, these relatively inductive clauses become inductive. Eventually become inductive, and therefore this forward propagation is a very critical and very significant insight that Aaron Bradley had, in hastening the convergence towards an inductive invariant when combined with this CTI elimination, which is already being done in all other inductive methods. You combine that with this learning inductive clauses and using that to also strengthen these frames so that you will get to an inductive invariant that is strong enough to prove the property. Okay, so yeah, in summary, 3 critical ideas. Okay, one is that it keeps multiple candidate invariance frames so that it can reduce all the SAT checks to single involving single transition things, and then it does elimination of counter example to induction by strengthening, and then in addition it learns certain relative inductive clauses which it uses. Okay, so these are the 3 things. Yeah. Okay, so we will see more details later on. Any general questions? I mean, I know that there's a lot of material, so I will let you. And I mean, if there are questions, okay. So I hope I did not go too fast. I mean, but anyway, we will. After you review my lecture, and then, so if I made any mistakes or if there are things that are still not clear, you can always come back in the next class. And then, so I will go through the details of the algorithms and, maybe some tips towards what needs to be implemented and so on, so that you can start thinking about it jointly about implementation. And I'll have Diganta also in the next class, so we can brainstorm some technical issues towards implementing it. Yep. Okay. Any questions?
So I have a slight question. So here, this representation of the frames is by some SAT CNF formulas, right? So can we do that by BDDs? Is that in any way any better or worse? As in keep the guys as BDDs?
No, because they're using SAT solvers. No. What is the?
No,
I don't think you could use. I mean, you can use what you're saying is, why not keep them as BDDs? And of course, you can check. You can do things. Huh?
Yeah, I mean, I don't know if it will be more efficient. I think the point of the million small SAT checks being faster than a single million variable SAT instance, this point would. I don't know how that would transfer to the BDD situation, but yeah, this sort of, it seems like we're working with sets, and that's why it felt like
This one thing is true though. All these frames are formulas ranging over only the SAT variables. Okay, I mean they're over approximations of images. Okay.
Yeah.
Therefore, they are predicates over a single instance of the state variables, unlike TS. That is true.
Yeah.
So your question is, why not keep them as BDDs?
Right.
You could.
Are there any implementations that do that? Or
no, I mean, most of them use SAT. Okay.
I mean, SAT.
I think it is because, see, there is one thing though. See, there is. I mean, although they are, you strengthen. I think, and here is the reason I believe. Okay. Well, in SAT, these formulas, if they are close to each other, when you do some of these checks, you can use incremental SAT. And that is something that you have to go through at some point. So there is no similar concept there, no, in BDD. Right. So that is a big, win here. So when you do something on this and again on this, and you keep doing again and again, these frames are kept forever. And therefore, if you've already done some checks prior to this, then, you can actually keep that state, okay, of your SAT solver. And so there's a lot of exploitation of increment satisfiably, which you will use. And I think that's what will gain. Okay, and therefore there may not be any similar advantage when you keep them as BDDs, and therefore maybe that is, yeah.
Right. I see. Yeah, that is actually yeah. So yeah, so that can probably lead to a lot of performance like boost, which
Yes.
will not be there.
Yeah, I think that's yeah. But I don't know if there are some BDD based checks things, but mostly that I know are all SAT. Okay, any other questions? Okay, then I'll see you Wednesday. Please do review these slides and lectures. So, and jot down points that I might have missed or not explained properly, or even made mistakes. Okay. Yeah. Okay. See you. Thanks, Diganta, for
Yeah. Thanks.